Welcome to the 2019-2020 Rocket Propulsion Design Team summary video. I'm David Arstein and I'm going to give you a brief introduction, summary, and conclusion for this project. The goal of the project is to create a rocket propulsion system that could eventually be made into a propulsion system for a small rocket designed entirely by NDSU's Mechanical Engineering Department. The rocket is a hybrid rocket design and, in this case, uses gaseous oxygen as oxidizer and acrylic as the combustion chamber, which also serves as the fuel grain. This means that as the rocket fires, the inner walls of the combustion chamber burn with the oxygen to produce thrust. The main advantage of a hybrid rocket engine compared to liquid or solid propulsion systems is safety, as well as the ability to throttle. The oxidizer and fuel are kept separately and must be intentionally mixed for combustion to occur, which makes the hybrid rocket design very safe. Also, the rocket can be throttled by controlling the flow of oxidizer. Here is an overview of our hybrid rocket design, which consists of 4 main components, which I'll cover in the direction of flow. The pre-combustion chamber is where the gaseous oxygen enters the rocket. From there, it flows into the combustion chamber, where the inner walls, in our case acrylic, burn with the oxygen, a reaction that has a lot of gaseous products and creates a lot of flow. From there, the combustion products travel through the post-combustion chamber and through the nozzle. The nozzle is a flow restriction, which makes the pressure build inside the rocket. When enough flow is created, the flow will reach sonic velocity at the nozzle throat and will increase to supersonic speeds as it passes through the diverging section of the nozzle. Acrylic was chosen to use as a fuel grain because it's strong enough to also serve as the combustion chamber, and it allows for optical access to the combustion reaction. The rocket and test stand were both designed and built completely. The rocket was unable to be tested due to the COVID-19 shutdown. There were a lot of calculations involved in the design of the rocket, so before the rocket was built, a simple scale prototype was made and tested to validate the calculations and design process. 2 scale rocket tests were completed. In the first, it was proven that the tapers and tie rods used to seal the combustion chamber were effective. There was no throat erosion observed in the mild steel nozzle, and the fuel regression rate was uniform along the length of the combustion chamber. One observation was that after the test was complete, the heat stored in the post-combustion chamber made the acrylic melt and droop slowly. The nitrogen purging in the full-scale rocket will cool the system much more quickly than in the small-scale test, so this is not a significant concern. In the second test, a propane spark ignition system was implemented, filters were used on the camera, and pressure was allowed to increase to a much higher value. Mock diamonds were observed in the exhaust, which is confirmation that the exhaust is supersonic. This was a major success because it strongly validated the design process and calculations. Sparks were observed in the exhaust of both tests, and the acrylic melted in a similar manner. After this test, some slag was observed on the nozzle even though it chipped off easily, and there was no measurable throat erosion. Both of the scale tests were major successes. Unfortunately, the full-scale rocket was not able to be used, but it will be tested this summer or next fall. Thanks for watching.